We're continuing our discussion of the impact of structure on acidity. In the last presentation, 2.4a, I talked about the element effect, and I'll summarize that here, but I'll talk about the next three below: the hybridization effect, resonance effect, and inductive effect. So in any case, in summary, what we talked about before, that is, if you go to the right on a column, the conjugate base is more stabilized by the element that's losing the proton having more electronegativity. So fluoride is more the F minus is more electronegative than the O minus, and therefore the HF is more acidic. More stabilized conjugate base, stronger acidity. And so we talked about that. We said that there was an energy component of that, and that's what the bottom left is about. But the take-home message here is that if the proton is being lost from an atom, if we think about a couple of atoms in a row, then the one that's going to be the atom that's losing a proton, if it's more to the right on the periodic table, it's going to be a stronger acid. And we also looked at going down a column, and we said that the stronger acids are going to be the ones that are where the proton is being lost from the atom further down the column. And this is because of the stability of the conjugate bases having to do with the size of the conjugate base. So the bromide is a bigger size than the chloride, for example. And so therefore HBr is more acidic than HCl. And we summarized the table of this for that in the last presentation. That is, we go to the right, the acids are increasing. We go down a column, acids are increasing. I'll remind you, we cannot we cannot make predictions based on diagonals, only in a row or a column. So the next thing we're going to talk about is hybridization effect. Here we're going to lose a proton from the same atom, but that atom may have different hybridizations into different acids. And so we're going to consider several acids in this particular case, three of them, and these are hydrocarbon acids. So we're going to lose a proton from hydrocarbons. First one is alkane, pKa is 50. Second one is alkene, pKa is 44. Notice we're losing a proton from a carbon of a carbon-carbon double bond. It's sp2 hybridized rather than sp3. Higher percent S character. Now we lose a proton in the next one from an alkyne carbon, and pKa is 25. We become much more acidic, and so the hybridization of the carbon of the conjugate base is sp, so it's 50% S. And so the take-home message here is that the acid with the greatest, that the conjugate base that has the greater S character is going to be more acidic. And so the most acidic of the three that are shown is going to be the alkyne proton. That's going to be the most acidic, followed by the alkene proton, and the alkane proton is going to be the least acidic. And I want to remind you something that you should learn in general chemistry. The weaker the acid, the stronger the conjugate base. And so that means that the alkane anion, that is the carbanion from the top row, is going to be the strongest conjugate base, and the weakest conjugate base is going to be the one at the bottom. So there's a greater acidity for propyne, and that's indicated by the pKa, and that's because the conjugate base is more stable because the carbon that bears the negative charge has more S character. And the more S character of the carbon, the more stability. We say that more S character, the carbon is going to be more electronegative, so it's more stable when bearing the negative charge. And the final thing that we need to say about this is, every time you see in a question like this, if you're losing protons from carbons, you have to look at the hybridization. If you're losing protons from nitrogen, you should look at the hybridization as well. It isn't just this example you should look at. You should analyze everything according to this. The next effect is going to be the resonance effect. Here the proton is being lost from the same atom, but in one case the conjugate base is stabilized by resonance, and the other case is not stabilized by resonance. So let's compare two oxygen acids. We have the ethanol at the top, and so the pKa of ethanol is 16, and below that we have acetic acid. The pKa of the carboxylic acid is 5 in this particular case. The pKa's tell us about the Ka's, and the Ka's we can calculate KEQs from Ka's But in any case, in both of these cases, they're strongly endergonic reactions. That's uphill energetically. The starting materials are much more stable than the products. And so these are strongly favored to the left. But the important thing here is that the carboxylic acid is not as strongly favored to the left as the alcohol in the first expression is, and that's because the conjugate base of the acetic acid, that conjugate base is stabilized by resonance, which we've talked about before. And so I've shown you the arrows and drawn in the resonance forms. That conjugate base is stabilized by resonance. But the ethanol conjugate base, which is the ethoxide on the right side of the upper equation, that's not stabilized. The electrons are localized on that oxygen rather than delocalized, as in the example below. So in the second example, the conjugate base is stabilized by resonance, and therefore the acid that gave that conjugate base is more acidic. And let me comment on this. This delocalization is important because just like for delocalization in bromide versus chloride, the bigger the atom, the more delocalized the electrons can be. Here we're spreading out the charge over several atoms, over two oxygen atoms. And so this is a more stable situation because the electrons are delocalized, which is entropically more stable. And the last one is going to be the inductive effect. The inductive effect occurs when nearby electron withdrawing groups are pulling electron density through the sigma bonds and stabilizing conjugate bases. So we'll see examples of exactly what I mean here. So the electron delocalization here occurs through sigma bonds because of electronegativity differences. We're going to be stabilizing the conjugate base again, but here because we have electron withdrawing groups removing electron density from the A-. So the first example of this, we're going to show the acetic acid, which we've shown before. It's drawn a little bit different here, but it's the same thing, pKa of 5. I'm drawing the conjugate base, the conjugate base resonance forms, which we've drawn before. The inductive effect is an example of that is having a chlorine rather than a hydrogen on the carbon next door to the carboxylate, that is the CO2 minus. That chlorine stabilizes the CO2 minus, and so the pKa becomes 3.3 rather than 5. It is more acidic than the example up above because the chlorine is stabilizing the conjugate base. If the chlorine is a little bit further away, it's a weaker inductive effect. That is, however that electron, the carbon-chlorine bond is influencing the stability of the carboxylate, however that's happening, if the carbon-chlorine bond is further away, the stabilization is less, and so the pKa here is 4.5. If we look at another example, now we have a fluorine bonded at the carbon next to the carbonyl, and the pKa is 2.6. That fluorine has a stronger dipole, has a stronger electronegativity, and therefore it's going to be pulling electron density more in its direction. This is one way to look at it. There's a second way I'll talk about, but in each of these cases, we have an electronegative atom pulling electron density away from the carboxylate, making it more stable, and therefore the acid is more acidic. And so the inductive effect is often drawn in terms of dipole interactions. That is a dipole interaction with the conjugate base anion. So let's draw those dipoles. There's a dipole for the carbon chlorine. It's a similar dipole for the carbon chlorine below, but that dipole is further away, and therefore it has less effect. For the carbon fluorine bond in the last example, that's a big dipole, so it's having a big effect on the negative charge. So the second way to think about that is that the positive end of the dipole it has an interaction with the negative charge of the carboxylate. That's an ion dipole interaction, positive near negative, that's stabilizing. So we're stabilizing the conjugate base by inductive effect. You could say the inductive effect is either electron withdrawing or it's an ion dipole effect. Either one of those is okay with me. But the carbon chlorine pulls electron density away to stabilize the conjugate base, or there's a dipole ion interaction which is stabilizing the conjugate base. That's saying the same thing as far as I'm concerned. So sometimes the acidities have to do with multiple effects, and I'm hesitant to bring this up because we never ask you for multiple effects, but I want you to know that they exist. Typically, things are not as simple as we often talk about in organic chemistry. Things are much more complex, even for simple molecules. And so for ethanol, this is well explained by the acidity is well explained by one effect for ethanol, for example, the element effect. But if we look at the acetic acid below the conjugate base is stabilized by resonance, but there's also an inductive effect going on because of the electron withdrawing carbonyl. There's a hybridization effect going on because the oxygens the hybridization is different because of the resonance forms. Come and ask me about this if you'd like to talk about it some more, but it's not so critical. We won't be asking you to analyze these kinds of issues on exams. For phenol, there's a resonance effect, an inductive effect, and a hybridization effect as well. Think about what those means. It's often difficult to discern which is the major effect if several effects are going on. But what you should do is to say, oh, the element effect is going to be huge, and the hybridization effect is going to be large. Resonance effect is going to be important. Inductive effects are weaker. And so whatever the most important effect is that you think, that's what you should say is the most important factor. So let me summarize the factors that influence acid strength. There's the element effect, and this has to do with comparing the acidities of acids that are in the same row or the same column. There's a hybridization effect. This is comparing acids where we're losing a proton from the same atom, but the atoms in the two examples of the acids are different hybridizations. There is the resonance effect. This has to do with stability of the conjugate base associated with resonance stabilization. All of these have to do with stabilities of the conjugate bases. And the inductive effect, this has to do with the stability of the conjugate base due to electron delocalization because of electron withdrawing groups through the sigma bond networks.